So again, this is Dr. Viv, and I'm here to talk about moments of inertia. This is part 2 of the two-part video. In part 1, I set up the moment of inertia in general and showed how it works out for a uniform density rod. And in this sequel, I'll talk about the moments of inertia of a non-uniform rod. So let's try the following example. First of all, let's say the rod is not pivoted about the end anymore, but take a new example where the rod is pivoted about some central point like that. Central axis, I should say. Moments of inertia are always about an axis. So in this case, it would be a rod trying to do this about this axis. So let's just call this the y-axis again, and that's the x-axis. And we'll take some lambda distribution. Lambda of function of x is equal to some constant term, lambda naught, plus another term which I'll call a times x. Okay, so that's an interesting looking density. It means that it's a fixed amount, so it doesn't go to zero anywhere. And on this side it increases, and on this side it decreases because x is negative from let's call this rod length L. So we place it right in the middle. So x is going to be positive, and we'll take the constant a to be bigger than 0 here. And we'll make sure that the density doesn't go to negative, so we'll adjust this constant a so that the density never goes less than 0. So anyway, assuming that condition is valid, we can find the moment of inertia of this object. So let's try doing that. The same setup. So you take this little mass element, we'll call it dx in length, and because that's lambda, the mass of the object is dm, which is lambda of x dx. That's the mass of the element. So we can find the integral just as we did before. Iy is going to be the integral from negative L over 2 to positive L over 2 x squared dm. And now I'm going to substitute for dm. Multiply through. At this point you can integrate term by term. So in the first case it's just lambda naught, which is a constant, and the integral of x squared is x cubed over 3 with the limits minus L over 2 and L over 2, and the second term would be the constant a times x4 over 4. These limits can then be evaluated, so I get lambda naught over 3. L over 2 cubed is L cubed over 8, and minus negative L cubed over 8, and this is going to be a over 4 times L to the 4 over 16 minus, now if you take negative L over 2 and take it to the power 4, you'll still get a positive number. So this will actually cancel out, and this will actually add. So I'm going to get lambda naught That's L cubed over 8 plus L cubed over 8, which is L cubed over 4. So that's lambda naught times L cubed over 4 times 3, 12. Now let's put this in terms of the mass like we did in the previous example. So the total mass of the rod is integral minus L over 2 to L over 2 dm. So that's going to be lambda x dx. That's what dm is. dm is lambda x dx from here. So I'm just going to copy that. Now I'll proceed to evaluate this integral. It's lambda naught times, the integral of lambda naught is just lambda naught times x between the limits. And this is a x squared over 2. Now x squared over 2 is even, just like that. So this will make no contributions. Just like that made no contributions. So the only contribution comes from this one. So that's going to be lambda naught L over 2 minus negative L over 2. You see this double negative phenomenon happening here also. And this gives me lambda naught L. So I can finally write my moment of inertia in terms of the mass. So that's here. What I'll do here is I'll take lambda naught L common. So outside, I mean, and then L squared, and that's 1/12 ml squared. So that's a pretty surprising result, I imagine, because this is exactly the moment of inertia of a uniform rod of mass m. So I'll write here, same as moment of inertia of a uniform rod. That's somewhat surprising because starting out, even I did not realize this would be the case. It takes as much effort to rotate this rod about the central axis as it would a uniform rod of the same mass. Well, thanks for watching, and I hope you understood how to find the moment of inertia of a non-uniform distribution through integration.